Hello everyone. Today we're going to talk about more hypothesis testing. Now we're going to be talking about when you have two samples. And so we'll be comparing two samples from two potentially different populations. We're going to cover three main hypothesis tests. When you have two proportions, you have two samples and each one has a proportion, and you want to say something about the two populations from which the samples came. And then you've got two means, and you have two independent samples, one from each population, and you want to say something about how the two population means may differ. And then we're going to talk about two dependent samples, where you have matched pairs. That's a very useful test. Inference about two proportions. It'd be nice to motivate this with an example. You have two professions, teaching and legal services, both very broad professions, and you want to know, does one have more women than the other? You take a sample from teachers, good random sample, and a sample from legal workers, and you get a proportion from each sample. The proportion may differ, but does it differ significantly? And we can do a hypothesis test to determine whether the difference in proportion is significant. P1 is the actual population 1 proportion. So the actual percent of teachers that are female. That's the true proportion. We don't know what that is. N is the sample size. X1 is the number of successes. That just means the number of how many people make up that proportion. So that in this case, number of women. P hat is the proportion, and Q hat is the complement. We do the same thing with the other population. Hypothesis testing follows the same framework. It's easier because the null hypothesis is given. All right, so to start off with, we first identify the claim, and then we negate the claim, and then we choose a null and alternative hypothesis, and the null hypothesis will always be that they're the same. Now that may or may not be the original claim. You still need to figure out the alternative hypothesis. May be you only have a few choices. It's either not equal to P2, P1 greater than P2, or P1 less than P2. You determine your significance level exactly as before, and then you identify the test statistic. I'm going to give you the test statistic right here. This is the test statistic you will use for this sort of a test. There. P here, this is called the pooled proportion. Notice it is the proportion of women in both professions. Successes among both samples. It's the best guess, assuming the proportions are the same. This indicates the null hypothesis assumption. We're assuming this. If that's the case, then they're both going to equal P hat. And then we find the P value. It's normally distributed, so no degrees of freedom to worry about, and then make a determination. We restate the decision in non-technical terms. Certain requirements need to be met. First, the sample proportions are two simple random samples. They have to be random. If you only sampled teachers from an all-girls school, the number of women is going to be much higher. If you sampled lawyers from a legal service firm for women, that's likely going to have more women working there. Those would be bias samples, and you can't infer anything from those. The two samples are independent, and this is necessary. So what does that mean? That means samples are independent if the sample values select from the population are not related in any way from each other. And then we need each of the two samples. For each of the two samples, there needs to be at least 5 successes and at least 5 failures. If I sample 100 lawyers, at least 5 need to be women, and no more than 95 can be women. That's a requirement for this theory to hold. The hypothesis test and pooled proportion for tests of hypothesis made about two population proportions, we consider only tests having a null hypothesis of P1 equals P2. With the assumption that P1 equals P2, the estimate of P1 hat and P2 hat are combined. make the best estimate of the common value, assuming the null hypothesis. All right, let's take an example. The proportions of cars with rear license plates only are the same in Connecticut and New York. Connecticut and New York are contiguous states. That means they touch, both having laws that require front and rear license plates. The proportion of Connecticut cars with rear license plates is 239 out of 2,049, or 11.7%. The proportion of New York illegal cars with rear license plates is only 9 in 500, so that's 1.6%. The sample percentages of 11.7% and 1.6% are obviously different, but are they significantly different? Or is that just chance? So we're going to answer this thing, but before we do, let's identify this data here. So we're talking about number of rear license plates. And so this right here is X1. This will be X2. This will be N1. This will be N2. Here's P1 hat. So that's successes over total, which is this, always as a decimal. Don't use a percentage in an equation. And then this here is P2 hat. Okay, and they're giving us the 0.05 significance level of the p-value. The p-value method is the only method we use to test the claim that Connecticut and New York have the same proportion of cars with rear license plates only. All right, let's get Excel open. On the Canvas app, you'll see in the home page there's a spreadsheet that you can download. I have downloaded that and shared it to Excel, and this is what I'm going to use. Step 1, the original claim. New York and Connecticut have the same portion of legal cars. Okay, the notation for that one is P1 equals P2. All right, step 2. What's the opposite of that? It's not saying Connecticut has more or New York has less. It's saying they're equal. The opposite of that is P1 does not equal P2. Step 3, the null hypothesis. For two sample proportions, the null hypothesis is always P1 equals P2. That's what we're testing. That's what we're going to assume. The alternative hypothesis in this case is going to be P1 not equals P2. All right, that's step 3. Step 4, identify significance level. Alpha equals right there. All right, go back. Let me go like this. That's nice, because I'm going to want my test statistic. Step 5 now is test statistic. It is given in the above slides. Maybe I'll just write it in. I'm going to write this in. Z equals P1 hat minus P2 hat over square root of P pooled, Q pooled over N1 plus P pooled, Q pooled over N2. Square root of all that. There's my test statistic. P pooled is X1 plus X2 over N1 plus N2. Alrighty, that should be enough. I'm going to need a few things here. I'm going to need X1. I'm going to go back down to my data here. Now, X1 is going to be 239, because that is the number of successes. Successes in this case are the cars with only rear license plates. N1 is going to be 2,495. X2 is going to be 9. And N2 is going to be 550. Great. That allows me to have P pooled. P pooled is X1 plus X2 divided by N1 plus N2. Enter. There's my pooled proportion. Now I need Q pooled, and that's going to equal 1 minus P pooled. p hat 1 is going to equal x1 divided by n1. Enter. P hat 2 is going to equal x2 divided by n2. Enter. All right, great. Now that I've got all that junk, I can put it all together and make z. That's p hat 1 minus p hat 2 square root of parentheses. Or p pooled times q pooled divided by n1. Close parentheses plus open parentheses p pooled times q pooled divided by n2. Oh, that's x2. n2. There we go. Close parenthesis. Enter. 7. Quite a z-score. Let me look at that again. Notice how I could click on it and see exactly what happened. On an exam, on the next celebration of knowledge, you will certainly need to do something like this, an Excel spreadsheet. You will lose points if I cannot click on the cell and see your formula. Make sure I can do that. All right, step 6 now is to find the p-value. It's normally distributed. P-value is going to equal, okay, now it's a two-tailed test, so I need 2. Here's my bell curve, and I'm way over here at 7 standard deviations. Now it is a two-tailed test because of the not equals to. I want this area and this area. I'm going to find this area first. I'm going to find this area and I'm going to double it. Now the z value corresponding to that area is negative because it's less than the mean, which is 0. Z values are always standard normal. Mean of 0, standard deviation of 1. So I'm going to use negative 7.07. It's exactly the opposite of this one. And I'm going to find my area to the left using norm.dist. And I'm going to multiply that by 2. All right, equals 2 times norm dist negative z-score, comma, 0, 1, cumulative 1. Close parentheses, enter. There's my p-value. If the p is low, the null must go. Reject the null. All right, now I'm going to put it all together. Step 8, I reject the null, so that means there is sufficient evidence to conclude that the two states do not have a equal proportion of cars with both front and rear license. All right, there it is. I have completed this hypothesis test. So, inference is about two proportion requirements. We are here. Okay, so here's the interpretation according to the author of the book from which I took this example. We must address the claim that Connecticut and New York have the same proportion of cars with rear license plates only. Because we reject the null hypothesis, we conclude that there is sufficient evidence to warrant rejection of the claim that the two proportions are equal. That is, there is sufficient evidence to conclude Connecticut and New York have different proportions of cars with rear license plates only. It is reasonable to speculate that enforcement of license plate laws is stricter in New York than in Connecticut. Connecticut car owners are less likely to install front license plates. Okay, what can we do when requirements are not satisfied? Bad samples are bad samples. If the sample wasn't taken well, there's no amount of statistical trickery that's going to fix that. If we violate the requirement that each of the two samples are at least 5 successes and at least 5 failures in a hypothesis test, we can use Fisher's exact test. We don't have time to talk about that in class, but that's something that you could certainly look up. Given your training in this class, may be able to implement. If we violate the requirement that each of the two samples has at least 5 successes and at least 5 failures in a confidence interval, we can use bootstrap resampling methods. Let's go on now. Means. So we talked about proportions, now we need to talk about means, independent samples. Two samples are independent if the sample values from one population are not related in any way to the sample values from the other population. The opposite of that is dependent. two samples are dependent or consist of matched pairs if the sample values are somehow matched based on some relationship. If one sample is husbands and the other sample is their wives, that is a matched pair. Another example of matched pair is you have students before a treatment and the same students after a treatment. The population of each is regarded as different because something potentially affected that. The students before are not exactly the same as the students after. I mean, they're the same person, but they're different in a way. Okay, notation. 2 means is the average salary of teachers greater than that of people in legal services. Are they greater or pretty much the same? Comparing 2 population means. Okay, so you have mu1 is the population, the actual population mean, which we do not know. The actual population mean of the first population, and one's the sample size of the first from the first population. X bar is the mean of the sample from the first population, and so on, right? We can read that. Okay, now what is this? Let's do the 8 steps here. Identify the claim, negate the claim, identify the null and alternative hypothesis. Now the null hypothesis, again, it's given to you. It's just going to be that they're the same. Are they the same or different? Is the average GPA of Harvard different than the average GPA of Yale or Dartmouth? Are they different or not? Then we talk about the significance level, which is usually given, but if it isn't, we use 0.05. And then you need to identify the test statistic. And this is the test statistic you will use. Okay, then we find the p-value. The p-value is a probability, so you use the distribution. In this case, a t-distribution with the degrees of freedom. There is a more sophisticated equation for degrees of freedom, but it is very complex. This little heuristic, take the smaller of 1 minus the 2 sample sizes, is very easy to compute, and it's fairly close and useful and conservative. Conservative, meaning it errs on the side of a type 1 error. It's more likely to do a type 1 error than a type 2 error. Once we've computed our p-value, we make our determination and we restate. Requirements. Sigma 1 and sigma 2 are not known, and we do not assume they're equal. That's requirements for the above theory. The 2 samples are independent. They're not matched in any way. Samples are simple random samples. Simple random samples. You also need large enough. The samples need to be enough. So the 2 sample sizes are both large, as to say they're both over 30, or both samples come from populations having normal distributions. That would also be it. All right, let's take an example. Listed on our student course evaluation scores for courses taught by female and male professors. Use a 0.05 confidence level to test the claim that the 2 samples are from populations with the same mean. Basically, course evaluations for courses with female professors is the same as that of courses taught with male professors. Does there appear to be a difference in evaluation scores of courses taught by female professors and male professors? Let's go to our data. I'm going to course evaluations. This one's got a lot of data to comb through. First thing, I'm going to select all of this. I would like to make my 2 samples. Shift, that worked. Now, data, filter, show filter buttons. Great. Now, professor gender, that gives you the females and the males. Great. And now I need my, okay. Then we have the course evaluations in that column. Let's get started here. Step 1. What's the original claim? The original claim is I think they're equal. To test the claim that the 2 samples are from the same population, so we're saying that they're equal. So this is going to be the same population, so that means that the mean is the same. So this is mu1 equals mu, that's my original claim. The negation of that, the opposite when that is false, is that mu1 does not equal mu2. Enter step 3, the null hypothesis. The null hypothesis is given mu1 equals mu2. We want to know if that's the case. And the alternative hypothesis is mu1 not equals mu2. Step 4, level of significance. Alpha equals 0.05. Step 5, test statistic is given in the slides. T equals x bar 1 minus x2 bar over square root s1 squared over n1 plus s2 squared over n2. Notice that because mu1 and mu2 are the same, my true mean is mu1 minus mu2, and that equals 0. So some books you will see they have this written out. I don't see what the point of writing that in is exactly, because we assume that the difference between those is 0. Okay, so there's my test statistic. Let me start getting what I need. So what do I need first? I guess I need x bar. I'll just say x1 will be the course evaluations with female professors, because those are on the top. Here I go. Okay, that's them. Is it going to tell me how many there are? I wish it would. Oh, I forgot to do equals. Well, let me just look and see. So that's from 2 to 41. All right, so x bar is going to equal average from B 2 to 41. All right, there it is. So that's x bar. N1 equals, what is N1? I'll do count. That's what I'll do. I'll go like this. I'll take this formula here. I will recycle it. Command V, but rather than count, 40. Great. S1. And so that is going to equal ST dev S, because it is a sample. And then what I'm going to do, I'm going to go Control V. I'm going to paste that, but I'm going to, cell, come on, get rid of that. Oops, okay. I think that's it. Now let's do the same for the other ones. Command C, Command V. This is going to be X2, N2, S2. That looks good. Now let's talk about the male professors here. So that is going to be from 42 all the way to 94. All right? 42 to 94. I'm just going to write that in here. B42 to B94. Great. B42 to B94. Copy that. Command C. Enter. 53. Okay, and there we go. All right, so there's that, what I need. Now I'm going to do T equals, put it all together, X bar, equals X bar minus X1 bar minus X2 bar. Oh, I forgot my parentheses left. All right, there we go. Got my parentheses. Divided by square root of S1 squared divided by N1 plus S2 squared divided by N2. Close parenthesis on the square root. -2. All right, step p-value. It's a t-distribution with degrees of freedom of the smaller of n minus 1 and n minus the other. Degrees of freedom is 39, because 39 is n1 minus 1 and smaller than n2 minus 1. So now the p-val is going to equal, and again, it's a two-tailed test. So times t dot diff, it's a negative value, so the left tail here, degrees of freedom will be that one right there, Cumulative is 1. Continuous distribution, cumulative is always 1. Press enter. Step 7. If the p is low, the null must go. The p-value is bigger than my alpha. And what that means is I'm going to fail to reject. Fail to reject. So, if I fail to reject, I don't get the evidence. So there's not sufficient evidence. The mean evals for male teachers is different from that of female teachers. There we go. All right. Great. So we did it. Now, there's a few situations I'd like to draw your attention to. The inference is about two means independent. This time, the sigma 1 and sigma 2, they're not known, but you're pretty confident that they are equal, that the standard deviations are equal. There's no reason they ought to be different. So if that's the case, then you have this, you do this with the same notation that we've been using before, but now you have a pooled estimated standard deviation, and then you just follow this format. Notice the difference. In the test statistic, you have SP squared rather than S1, S2, and the degrees of freedom is also different. But other than that, it is exactly the same. Population standard deviations are almost never known, but if they are, the test statistic and confidence interval are based on the normal distribution instead of the t-distribution. I'm not going to demonstrate an example on this case just because it's not as important as the other ones. And then there's another case is where the sample standard deviations are known and equal. And if that's the case, you'd use the test statistic given here. Do we need to know degrees of freedom? No, because it's a z. It's normally distributed. So no degrees of freedom. You can find the p-value very easily. Just use norm.dist. Here is a fairly useful table. Notice you'll recognize some of the test statistics that we have already seen. This right here we've seen from chapter 9. This is also, wait a minute. Yeah, this is if the standard deviation is known. This one is if the standard deviation is not known. We're going to talk about this one next. That's the paired differences. Here's equal variance, which is called homoscedastic, and the heteroscedastic case when the variances are unequal. There's that formula for the degrees of freedom that I was telling you about. But I prefer to take the minimum of n1 minus 1 and n2 minus 1 to approximate degrees of freedom. One last thing, matched pairs. When designing an experiment or planning an observational study, using dependent samples with matched pairs is generally better than using two independent samples. Test whether a treatment improves. Just use the people before and after, and that'll be your matched pairs. Okay, so there's a bit of new data notation. D is the set of differences between the two values in the single matched pairs. Maybe it's a speed training, and you're interested at the distance of a mile. So mile time, the difference in the mile time of the matched pair. Before the treatment, I ran a 14-minute mile. After the treatment, I ran an 8-minute mile. The D would be -6, 14 to 8, -6. All right, and so you have a bunch of D's. You can find the mean difference of the sample. That would be D bar. Mu D, we don't know what it is, right? That's what we're trying to talk about. And the question is, on average, will everybody improve? Will D be positive or negative? What will D be? SD is the standard deviation of the differences, and N is the number of pairs of sample data. Here's the hypothesis test steps. In this case, I'm going to use D equals 0. That's my null hypothesis, and this is D hat minus mu D over SD square root n. That's the test statistic. It's a t-score, and the degrees of freedom is n minus 1. Let's take an example, and then we are done. Remember that actress and actors data? I have it on Excel. I didn't want to write actresses and actors, so I just wrote thespians, which is a fancy word for actors. Okay, well, where's my data? Oh, okay. Thespians. All right, here we go. These are matched pairs because they are the age of the recipients of the Best Actress, Best Actor, Best Actress awards in the same year. The first year was 1927. Both the 22 and the 44 are associated with 27, so they are matched. All right, let's go back and take a look at the prompt. Okay, so data list ages of actresses when they won Oscars in the category of Best Actress, along with the ages of actors when they won Oscars in the category of Best Actor. The ages are matched according to the year that the awards were presented. This is a small random selection of the available data so that we can better illustrate the procedure of this section. Use the sample data with a 0.05 significance level to test the claim that the differences have a mean less than 0. The difference between best actresses and actors, actresses minus actors, and the difference is going to be less than 0, are generally older when they win Best Actor. All right, let's go to our thespian sheets. First, this is all the data, the population here. I don't want to do this on a population, so instead I'm going to randomize it and take a sample. Insert a column, equals rand, fill it down, copy, Command C, drag, paste. There's my random numbers. Grab these, filter, sort smallest to largest. It mixed it up because it was 2242, now it's 2162. And so that's all randomized, and I'm just going to go ahead and take the first 30. Can I put that in a box? So that's the data I'm interested in. Unfortunately, it's going to be different from your data. See if we get the same conclusion. That's the point of this theory. You ought to get the same conclusion irrespective of the simple random sample. I'll be interested to see what conclusions we get. All right, step 1, the mean difference in ages between actresses and actors in the same year is negative or less than 0. Symbolically, what does that look like? Mu d is less than 0. Step 2, the alternative is mu d is greater than or equal to 0. Step 3, the null hypothesis is mu d equals 0. The alternative hypothesis is mu d less than 0. How did I know to do less than and not greater than? The greater than or equal to is the null hypothesis. The original claim goes to the alternative hypothesis. Step 4, alpha equals 0.05. Step 5 is the test statistic. There it is. You write it in. T equals d bar minus mu d, which is 0, over SD, standard deviation of d, n, divided by n. D bar is going to equal, so first what I need is my d's. The differences equals actress minus actor. Enter, copy, just the first 30, paste. Okay, there, pasted it. So there's my d's. The d bar is the mean of that, equals average, enter. Yours will probably be different, I don't know. We have d bar, mu d is assumed to be 0 because of the null hypothesis. SD is going to equal dot s, because ours is a sample, a little sample of 30 years. There's a standard deviation, SD. I need n. N equals 30. Okay, here I go. T equals parenthesis d bar minus 0 divided by parenthesis s divided by square root n. Enter. Negative. So the test statistic is negative. Our data is 2 standard deviations. We may be able to reject the null hypothesis in favor of the alternative. Let's make sure. Step 6, p-value now. Actually, I better get degrees of freedom. That's 30 equals 30 minus 1. Now let's do equals 30 minus 1. Okay, now I'm ready for my p-value. This is a left-tailed test. My t-statistic is on the left tail. All right, this is going to equal t-dist. Plug in my t, my test statistic, degrees of freedom, cumulative, and enter. Now my determination. Step 7, p is less than alpha. If p is low, the null must go. So I'm going to reject the null. Step 8, reject the null and get evidence. There is sufficient evidence to support the claim that the mean difference between actresses and who won best act and actress in the same year. If you subtract those differences, the same year, let's see what it says there, that the mean of those differences is less than 1, meaning in an average year, the best actor will be older than the best act. We can say that with 95% certainty. All right, everybody. That's all right. Have a wonderful day, and we'll see you later.